Welcome to our channel, and today we are going to help you understand the Paper Gorilla large language model connected with massive APIs. The text is about a study conducted by researchers at UC Berkeley and Microsoft Research to enhance large language models, LLMs, ability to make API calls. Despite their prowess in tasks such as natural dialogue and mathematical reasoning, current models like GPT-4 struggle with generating accurate inputs for APIs and may incorrectly use API calls due to a tendency to hallucinate. To address this, the authors present Gorilla, a fine-tuned Llama-based model that outperforms GPT-4 in writing API calls. In addition to its superior performance, Gorilla is adept at adapting to document changes, which enables it to handle user updates or version changes effectively and reduces the chances of generating inaccurate content. To assess Gorilla's capabilities, the authors created API Bench, a dataset featuring APIs from Hugging Face, TorchHub, and TensorHub. Gorilla, combined with a document retriever, demonstrates how LLMs can be improved to more accurately work with tools, stay updated with current documentation, and increase the reliability of their outputs. The researchers have made Gorilla's code, model, data, and a demo available online. The study indicates that by allowing LLMs to access and use cloud-based tools through APIs, LLMs could transform into primary interfaces for various web services and computational tasks. The text discusses the creation and evaluation of the Gorilla model, a machine learning model designed to accurately generate API calls for converting audio to text using TorchHub. The model is based on the Llama 7B framework and has been fine-tuned with a new dataset called API Bench. API Bench was constructed by scraping machine learning APIs from public model hubs like TorchHub, TensorHub, and Hugging Face. It includes a vast number of API calls, a total of 810 from TorchHub and TensorHub, and a curated set from Hugging Face. Capturing the complexities and overlaps that exist among them, several tests were carried out to gauge the performance of various large language models, LLMs, in generating correct API calls and minimizing errors. These LLMs included GPT-4 and Claude, alongside the newly created Gorilla. Through a process known as self-instruct, and by using retrieval methods that help the model find relevant API documentation, Gorilla was able to outperform its peers by selecting functionally correct APIs with fewer incorrect details, hallucinations. An example provided shows that while GPT-4 produced a non-existent model and Claude chose the wrong library, Gorilla made the right API call. Data suggests that Gorilla improves accuracy and reduces hallucinations across a wide range of tests. To conclude, the Gorilla model, with its retrieval-aware training, not only adapts to changes in API documentation, but also demonstrates an increased understanding and reasoning about the constraints and limitations present within overlapping functionalities of APIs. Summary: the text discusses recent advancements in large language models, LLMs, particularly in program synthesis and tool utilization. Much progress has been made by augmenting LLMs through prompting and fine-tuning. New open-source models like Llama, Alpaca, and Vicuna have improved our understanding and experimentation with LLMs. The paper presents Gorilla, a different approach that focuses on enhancing LLMs to handle a multitude of tools and introduces a novel concept of fine-tuning LLMs with information retrieval. Tool usage in LLMs has become more prominent, with Toolformer being a notable example. Many models integrate tools like calculators, translation systems, and interpreters. However, existing work has mostly been exploratory and concentrates on specific tools. This paper seeks to expand the use of a wide variety of tools, API calls, in a more open-ended and systematic fashion, which also includes systematic evaluation and building a workflow for future applications. In terms of program synthesis, various strategies have been explored to improve LLM's coding capabilities. These strategies have included in-context learning, task decomposition, and self-debugging. The paper's research diverges by focusing on the synthesis of linear programs using API calls, which simplifies verification and evaluation by operating at a higher level of abstraction. Methodologically, the paper introduces API Bench, a benchmark created from TorchHub, TensorHub, and Hugging Face API model cards. Data for the benchmark was collected from model cards across several platforms and domains, with poor documentation filtered out, resulting in a dataset consisting of models from multiple domains, including multimodal, computer vision, NLP, audio, tabular data, and reinforcement learning. TensorFlow Hub models were also filtered and processed. Gorilla, a novel training paradigm incorporating an information retriever, is presented along with a new evaluation metric based on AST, abstract syntax tree matching. Please note, the text is incomplete and cuts off at section 3.1 regarding dataset collection, where the process of curating models and the relevant API documentation is described. Therefore, the summary cannot include conclusions or findings that might be presented later in the original document. This text describes the creation and training of Gorilla, a system designed to enable large language models, LLMs, to interact with API calls. A dataset of API calls was curated, including 1,645 calls from 3 different sources: TorchHub, TensorFlow Hub v2, and Hugging Face. Using GPT-4, the authors generated synthetic instruction data to create instruction API pairs, which were used to fine-tune a Llama 7B model, the backbone of Gorilla. Gorilla can operate in 2 modes during inference, with retrieval and zero-shot execution. To generate instructions without revealing API names, the authors provided GPT-4 with in-context examples and a reference to API documentation. For each of the 1,645 dataset points, 10 instruction API pairs were generated. The training process involves turning these pairs into a user-agent chat-style conversation and then conducting standard instruction fine-tuning on Llama 7B. Gorilla is designed to understand API calls with inherent constraints, such as parameter size and minimum accuracy requirements. This introduces additional complexity and demands greater nuance from the LLM. The authors highlight the potential for using open-source alternatives to GPT-4 and describe the formatting of model cards for each API call, including fields like domain, framework, functionality, and example code. More detailed information is provided in an appendix. The text discusses the challenges of training large language models, LLM, to accurately interpret and execute API calls, while considering user-defined constraints, such as invoking an image classification model with specific parameter and accuracy requirements. It emphasizes the necessity to fine-tune LLMs to handle complex API call parameters and introduces a technique called retriever-aware training. To enhance the LLM's ability to adapt to changes in API documentation, improve in-context learning performance, and reduce errors caused by the LLM generating incorrect or imaginary hallucination information. The training method includes appending the API documentation in JSON format to the user prompt to improve the model's accuracy in responding to the first part of the user's query by understanding the second part of the query. However, the authors note that using retrieval doesn't always improve the LLM's performance. The paper also discusses Gorilla inference, where the model interprets natural language prompts in 2 modes: zero-shot, without prompt tuning, and retrieval, with up-to-date API documentation. Gorilla LLM then generates the appropriate API call. Furthermore, the paper describes the verification of APIs using AST, abstract syntax tree, subtree matching to ensure the API called by the LLM matches one in the dataset and is not an error or hallucination. The process includes matching the tree structure and arguments of the API call with those in the database, considering both required and optional Python arguments. Finally, the text touches on the system's ability to execute APIs, although that is not the main focus of the paper. The text discusses an evaluation of the performance of a model named Gorilla in making API calls, using a dataset created for benchmarking. Gorilla is compared to other state-of-the-art language models like GPT-4, GPT 3.5 Turbo, Claude, and Llama 7B in a zero-shot setting, where the model does not use any retriever and solely relies on the user's natural language prompt. Additionally, the evaluation explores the impact of different retrieval methods on the model's performance. These methods include the BM25 algorithm, GPT index, and an Oracle retriever. Retrievers are used to find the most relevant API documentation based on the user's query, which is then added to the prompt to aid the model. The text illustrates the use of TorchUtils Hub and TensorModel Zoo to load different DenseNet models, e.g., DenseNet 121, DenseNet 1sig1, and DenseNet 201 from repositories like PyTorch Vision and Hugging Face PyTorch Transformers. It provides examples of how to load pre-trained models using torch.hubhub.load and indicates that the parameter pre-trained can be set to either true or false. The evaluation also involves assessing AST, abstract syntax tree accuracy on API calls. The error rates for hallucination and wrong API selection are reported along with the overall accuracy. The evaluation is conducted on a holdout test set, which is part of a dataset divided into training and testing sets. Finally, there is a mention of analyzing API calls through AST subtree matching, demonstrating the process with a figure where the correct API call is confirmed by the presence of a matching subtree in the dataset, with the relevant part highlighted in brown. The text appears to be discussing the performance of different language models, LLMs, such as GPT-3.5, GPT-4, Claude, and Gorilla, particularly in terms of accuracy and how they interact with different retrievers. A retriever is a system used to enhance the capabilities of language models by retrieving relevant information to assist in generating responses. Key points from the text include: the Gorilla model is noted for outperforming other models on Torch Hub and Hugging Face and matching performance on TensorFlow Hub, even when compared to state-of-the-art SOTA models that are both closed and open source. The models were evaluated based on their ability to provide correct domain names, with the dataset not being exhaustive. Fine-tuning the Gorilla model resulted in superior performance over the baseline and other models, indicating that this process was more effective than simple retrieval. Introducing a non-optimal retriever at test time can decrease accuracy because it might misguide the model, leading to more errors. The results from the tables show that Gorilla consistently outperforms the other models across different settings. Experiments with fine-tuning a base model, Llama in this case, with a retriever resulted in significantly improved performance. There's a notable difference in performance between current retrievers and an ideal ground truth retriever, with the latter being much more effective. Fine-tuning with better retrieval systems shows promising improvements in model performance. Overall, the text suggests that fine-tuning language models with a good retriever can lead to substantial gains in accuracy, and that the Gorilla model, in particular, performs exceptionally well across different platforms. The text discusses the use of a language learning model named Gorilla, which has been trained to understand and react to updates in API documentation and changes in code. Here's a brief summary. The users want to automatically remove the background from images, and Gorilla responds with different API calls using deep learning models pre-trained on FCN ResNet 101 and FCN ResNet 50, indicating its ability to retrieve the necessary code to perform tasks. The text compares retrieval techniques, mentioning that Gorilla performs better with a retriever than without one, across various platforms, Torch Hub, Hugging Face, TensorHub. It also discusses hallucination errors, a term here indicating when models generate incorrect or irrelevant information, which happen less with zero-shot prompting with LLMs like GPT 3.5 compared to GPT 4. These errors are shown to be mitigated when retrievers are used. Lastly, the text highlights the importance of Gorilla's ability to adapt in real time to changes in the API documentation, ensuring it remains updated despite rapid technological advancements. The model showcases its capability to adjust API calls following upgrades, such as switching from ResNet 50 to ResNet 101, or when registry sources change, from PyTorch Vision to NVIDIA Deep Learning Examples Torch Hub, illustrating its flexibility and reliability in a rapidly evolving field.